Hello guys, a big thank you for supporting my channel. You have made me very popular and am grateful. Thanks to the students all over the world, especially Pakistan, India, Bangladesh, Rwanda, Zambia to mention but a few. You have been the greatest fans in my teaching career. Thank you for always watching my videos, giving suggestions on, asking questions, making constructive criticism and corrections. I love you so much and wish you success in your academics. Continue sharing the channel with anyone involved with Cambridge Physics. If you are new to my channel, please consider to subscribe and share and like the videos. Hit that like button and bell icon to keep updated. Thank you so much.
Hey guys, my name is IBM and this is going to be Simple Harmonic Motion. And I think this is going to be lesson 2 of Simple Harmonic Motion. I think this is going to be the last lesson. If you're a very serious teacher, you should teach Simple Harmonic Motion in 4 hours, I think. If you're very serious, you should teach it in 4 hours and then leave students to do a lot of practice of the solved past paper questions that I've recorded in the videos that I've attached in on that I'll actually be attaching at the end of each of these lessons. So this is lesson number 2. So this is lesson 2 of Simple Harmonic Motion, and today I want us to concentrate on basically examples of bodies or examples of bodies which approximate simple harmonic motion or examples of approximations of simple harmonic motion, and we shall also explore the energy of a body performing simple harmonic motion, and that will be the end of simple harmonic motion. So some of the examples we expect of oscillatory motion which approximate simple harmonic motion could include imagine a test tube bobbing up and down in water, a simple pendulum, a compound pendulum, a vibrating spring, atoms vibrating in a crystal lattice, a vibrating cantilever, a trolley fixed between two springs, a marble of on a concave surface, a torsional pendulum, liquid oscillating in a tube, a small magnet suspended over a horseshoe magnet as inertial balance. A small magnet suspended over a horseshoe magnet on an inertial balance, then a piston in a gas-filled cylinder, and so many others. So, of course, you cannot be asked to list examples of oscillatory motion that approximate simple harmonic motion. So for our learning purposes, to gain confidence with dealing with a simple harmonic motion and especially the definition of simple harmonic motion, we shall talk about the simple pendulum because that is common. We shall not talk about the compound pendulum. We shall talk about vibrating strings. Of course, atoms vibrating in a crystal lattice. These ones approximate simple harmonic motion, but we shall not talk about that. A vibrating cantilever, we shall not talk about that. Trolley fixed between springs, we shall discuss that. A marble on a concave surface is like this. So a marble on a concave surface, when released, it goes to the other end and keeps coming back like that. It oscillates. Then we shall not talk about a torsion pendulum. We shall talk about a liquid in a U-tube. We may not talk about a small magnet suspended over a horseshoe magnet on an inertial balance. We shall not talk about piston in a gas-filled cylinder. We may not talk about piston in a gas-filled cylinder. So let's try to explore at least some of these, at least 5 of these or 4 of these examples. And at least by the end of it all, we shall be able to understand what we are really talking about when we talk about examples of oscillatory motion which approximates simple harmonic motion. So these are some of the examples of such motions. By the way, an inertial balance really approximates a simple harmonic motion very well. Okay, let's begin with the first one. Maybe let it be the simple pendulum. So let's start with the simple pendulum. We are going to consider the motion of a pendulum bob of same mass m. We shall consider the motion of a pendulum bob uh, of same mass m suspended at the end of a light inextensible string of length. Let's say the length of the string is going to be L, fixed at one center, and we shall assume that the bob is given a small displacement, maybe to the right hand side or the left hand side, and then released. Of course, when it is displaced, it makes an angle. Let's say it is theta with the equilibrium position as shown here. So in this diagram, I have considered a simple pendulum as a string on which a bob has been attached as shown here. And it has been displaced through a small angle theta. Let's assume theta is very small and measured in radians. So it has been displaced. So number one, we notice that, or we know very well that there is a tension in the string, but we shall not mind much about that tension. We know that this object has weight which acts vertically downwards, and it must be the component of this weight pointing towards the center or towards the equilibrium position that is responsible for bringing this towards the equilibrium position. So if this angle, the angle with the vertical is theta, automatically this is also theta because they are alternating. When I make this longer, then of course the weight of the object normally acts vertically down. So this angle is theta. It's the same as the other one. So the weight mg has two components. One which acts as at a tangent to the circular path in which the object moves when it is oscillating, and one which acts perpendicular to that tangent, which is going to be mg cos theta. So if this angle is theta, resolving mg to the other side is mg cos theta. Resolving it elsewhere, it is going to be mg sin theta. Because this mg sin theta is a tangent to the circle which acts towards the center, it is the one which is going to be responsible for bringing the object back to equilibrium, and we are going to call it the restoring force. So in other words, mg sin theta is going to be called the restoring force because it tends to bring back the object to equilibrium position. Note that we can assume that the body had been displaced to the right hand side, so the displacement was in that direction. Therefore, the force tending to bring it back to equilibrium must be pointing towards the equilibrium position, so it is going to be in the opposite direction. And for that reason, we shall simply say that the restoring force F is going to be equal to negative mg sine of theta, because this is the force which is acting towards equilibrium position. So we can explain the minus. We can say the minus indicates that the force is in opposite direction to displacement. So the minus is in the opposite direction to displacement. That's why I've indicated it there. Then the next thing, we shall just consider theta as a small angle. So for small angles measured in radians, we know that the sine of the angle is approximately the same as the angle itself. But if we approximate the arc length here to be a straight line because theta is very small, then we come up with a right angled triangle. So we have a right angled triangle where x is going to be the opposite, the arc length, which is approximately a straight line if theta is very small. the arc length is going to be the opposite, and then L is going to be the hypotenuse. So that means sine of theta is equal to the opposite divided by the hypotenuse, which is L. But remember, theta is very small. That means you can think about sine theta to be approximately equal to theta. But even if I don't do that, I notice that F is going to be equal to negative mg, where there is sine theta, I'll put there x, then I divide this by L. So it means that force F is going to be negative mg over L times x. Then you recall Newton's second law. By Newton's second, when I write N2, that is Newton's second law. By Newton's second law, we have that the resultant force on an object is equal to the mass times acceleration. So this implies that MA is going to be equal to negative mg divided by L then times x. So m has cancelled out. So we say acceleration is equal to negative g over L times x. Remember, in one of the definitions or in one of the lessons, I mentioned that as long as the acceleration of an object follows the defining equation of simple harmonic motion, it will always be approximating simple harmonic motion. So we are saying that A is equal to negative g over L, where we notice that A is directly proportional to x. That's number one. G is acceleration of free fall, and L is the length of G is acceleration of free fall, and L is the length of the pendulum, which are constants. So since G over L is equal to a constant, it means acceleration is directly proportional to x. And there is a minus. The minus indicates that acceleration and the displacement are always in opposite directions. So we can simply just say that we can simply say that A equals negative G over L x is of the form. This is of the form A equals to negative omega squared times x. So if we compare the two equations, maybe we want to find omega, we want to find the period of oscillation, then we shall notice that therefore omega squared is equal to G divided by L. Remember, omega was given by 2 pi divided by t. So I can find the period. So it means the period t is equal to, omega is 2 pi over t. So when I substitute for omega, I'll have 2 pi over t, but this should be squared, being equal to G over L. When I get the reciprocal and then I square, I have that t squared over 4 pi squared is equal to L divided by G. So it means the period, capital T, is going to be 2 pi square root of L divided by G. So that will be the period. That will be the expression for the period. We may be asked to find the expression for frequency. So frequency is 1 over period. So we just get the reciprocal. So the frequency is going to be 1 over 2 pi square root of G divided by L. So many times you may not derive from first principle. They may quote this for you, or they may give you an expression such as this one here and ask you to derive an expression for period or frequency. Of course, they expect you to introduce Newton's second law, and they expect you to compare this equation with the general equation of simple harmonic motion. You should be able to find what omega is equal to, and then you should be able to use omega is equal to 2 pi divided by period. So that would give us the frequency and the period as required. So that is a simple pendulum. That would be a simple pendulum approximating simple harmonic motion. So you observe from the above expressions that the period of a simple pendulum is independent of the mass. When you look at the expression for period, it is not depending on the mass. Therefore, a big mass and a small mass, as long as the length of the pendulum is the same, the period is going to be the same. The period of a simple pendulum does not depend on the mass. It simply depends on the length of the pendulum. Whether you have a bigger mass or a small mass, the period is going to be the same. Okay, so that is a simple pendulum. If I wanted to sketch a graph of, say, t squared against L, I think that would be a straight line through the origin. You have that t squared is going to be 4 pi squared times L over G. So if I sketch a graph of t squared against L, I think that would be a straight line through the origin. A graph of t squared against L, that would be a straight line through the origin. And of course, the gradient of this straight line, if I try to find the gradient of this straight line, the gradient is going to be 4 pi squared over G. So the gradient would be 4 pi squared divided by G. If I sketched a graph of t squared against L, that would be a straight line, I think, through the origin. And the gradient or the slope of this graph is going to be equal to 4 pi squared over G. So we can find G from the slope for a simple pendulum. So, however, in practice, the graph that I've just sketched may not pass through the origin, as I have just stated it here, because there are a few things which may affect the motion of the pendulum. Number one, there could be air resistance, which later on we shall say it causes damping. A few things that could affect the graph from passing through the origin could be, number one, there could be air resistance. There could be air resistance. Number two, there could be an uncertainty in measuring the value of L. There could be an uncertainty in measuring the value of L. And number three, the angle of swing may be big. If theta is very big, for example, if theta is greater than 10 degrees, then of course we cannot assume that is a small angle if it is big. So it means the expression t squared equals 2 pi over times root of L over G would be affected if there is air resistance, if there is an uncertainty in measuring L, or if theta is greater than 10 degrees. However, in deriving this expression, we have assumed that the displacement is very small, so that theta is extremely small and measured in radians, and we have also assumed that the air resistance is negligible. Otherwise, if the air resistance is not negligible, then theta is not going to be constant, and therefore we cannot arrive at this expression. And therefore, we can also not say that the graph passes through the origin. However, if we assume these three are not, we assume there is no air resistance, we assume that there is no uncertainty in measuring L, and we assume that the angle is very small and measured in radians, then T is equal to pi root of L over G for a simple pendulum. Okay, so I think I've given my mind on a simple pendulum. Number two, I think for number two, let's talk about our floating cylinders. What do we mean by a floating cylinder? A floating cylinder. Of course, we expect a cylinder to be placed maybe on a water surface and it is made to float. That's what I'm calling a floating cylinder. So let's consider a cylinder which is initially floating at equilibrium in position A as shown by this diagram. So it is initially floating at equilibrium. The only forces acting on this cylinder are the upthrust and the weight of the cylinder. So at equilibrium, the upthrust upwards, which I will call U1, is going to be equal to mg. It is at equilibrium. And it is such that it is submerged with a distance L within the liquid at equilibrium. So we are going to assume, let us assume that the cross-sectional area of the cylinder is A. Let's assume the cross-sectional area of the cylinder is A. And remember, at equilibrium, I've mentioned that the upthrust is equal to the weight at equilibrium. And according to Archimedes' principle, the upthrust is equal to the weight of the liquid which is displaced. So the upthrust is equal to the weight of the liquid displaced. That is according to Archimedes' principle. So the upthrust equals to the weight of the liquid displaced. That is according to Archimedes' principle. So what weight of the liquid has been displaced in position A when it is just in equilibrium? So I'll simply say at upthrust U1, which is equal to the weight of the liquid displaced, which is equal to mg, is going to be equal to the weight of the liquid displaced. Mass is our cross-sectional area of the cylinder times L. The weight of the liquid displaced, the volume of the liquid displaced is equal to this volume of which has been submerged. So the volume, which is, of course, mass is density times volume. Mass is density times volume. The volume which of the liquid which has been displaced is equal to the cross-sectional area of the cylinder times L, which is inside the water. So this is going to be multiplied by G. So this is the weight of the liquid which has been displaced, and that is going to be equal to the upthrust. So I will call this one the first equation. Then if we now push the cylinder further beyond equilibrium position and release it, it can't stay there. Because when we push it further, we increase the upthrust. It means the new upthrust U2 is going to be greater than upthrust U1 is going to be greater than mg. The new upthrust is actually greater than the weight, so it can't stay there deeper because as you push this further, the upthrust depends on the depth of the submerged object, the depth or the height of the submerged object. The upthrust depends on the height of the submerged object because the difference in the pressure between the top and the bottom of the object. So if we dip an object further, the height which is submerged increases. It means the upthrust increases. So in the new position, the upthrust is greater, as you mentioned in your AS level physics. So the new upthrust U2 is going to be greater than mg. So that means there is an excess upward force. And that excess upward force is responsible for bringing the object or the cylinder back to equilibrium or restoring equilibrium. So the upthrust U2 is going to be equal to the mass. The mass, of course, is going to be now, the cross-sectional area has remained A, but the length, the height submerged has changed. So the cross-sectional area is now going to be A times the height submerged, which is going to be L plus X. So this is the volume submerged because mass is density times volume. Then we shall multiply this by G. That is, I'm using mg. So this is the volume submerged times G. Oh, I am forgetting the density. So I have to add the density here times the density because it's mass. Let me try to correct this. So the mass, the volume is cross-section area times L, then times density times G. So even here, it is the volume times the density, then times G. So we have just to compare, to simplify this. If I try to open the bracket here, it means that the new upthrust U2 is equal to A L rho G plus A rho G times X. So that is the new upthrust. So the restoring force is the one which takes back the object in equilibrium. So the restoring force or the resultant force, which is given by Newton's second law, the restoring force, I'll call it F, is going to be equal to, I will put a minus because it's going to act in the opposite direction to displacement. The displacement was downwards. When we remove the the pushing force downwards, the cylinder moves upwards, which means the restoring force was in the opposite direction to the displacement. So this is going to be equal to negative into U2 minus mg. The resultant force in its position B is going to be U2 minus mg. But remember, the rest towarding force F is given by Newton's second law, so I will say M times A is equal to the negative of the upthrust U2 is going to be AL rho G plus A rho GX. Then I will subtract mg. But remember from the first equation, upthrust U1 was equal to mg, which was AL rho G. So it means MA is going to be the negative of AL rho G plus A rho GX minus, where there is mg, I'm going to put AL rho G. So this is AL rho G. So this cancels with this one, and we remain with MA as being equal to negative A rho GX. So which means we have arrived at a simple expression such as acceleration is equal to negative A rho G divided by M times X. You notice that this is similar to an expression for a simple harmonic motion, but we could also simplify this as this could also be written as acceleration is equal to the negative of I think this could be written as, because we know that cross-sectional area times density over mass, we can simplify this to negative A times G divided by V, because we know density over mass is volume. I mean, density over mass is the reciprocal of volume, because we know density is equal to mass over volume. So density over mass density over mass is the reciprocal of volume, so that can be negative Ag over V, then times X. That is one way of doing that. Alternatively, we notice that density or mass equals to density times volume, and mass is equal to density times cross-sectional area times L, because volume is A times L. And we know that A times L is volume. So if I take L, I want to take L on one side, so I have 1 over L is equal to rho A divided by M. So 1 over L is rho A divided by M. So I can also write the expression for acceleration as where there is rho A divided by M, I will put there 1 over L. So this becomes negative G over L, then times X. So whatever way. Like I said, you may not be asked to derive all this, but the examiner will quote for you an expression. So the expression could be written in this form here, it could be written in this form here, or it could be written in this form here. But what is special here is that we should be able to notice that in all cases there is a minus. The minus simply indicates that acceleration and displacement are always in opposite directions. The cross-sectional area of the cylinder is constant, the density of the liquid is constant, G is constant, the mass is constant. So the whole of this is a constant. A rho G over M are constants, which means acceleration is directly proportional to displacement. So acceleration is directly proportional to displacement. There is a minus, hence that is simple harmonic motion. Our task now remains for us to find the frequency and the period where necessary. So I'll not use all these expressions, I'll just choose one of the expressions to find maybe the period. I'll use only the first expression which I derived. So comparing that with omega, acceleration is equal to negative omega squared times x. So it means omega squared is equal to A rho G over M. Remember, omega is 2 pi over t, so I'll say 4 pi squared over t squared is equal to A rho G over M. I'm trying to find an expression for the period. So the period is going to be, we get the reciprocal both sides and find the square root. So it is going to be 2 pi under square root of M divided by A rho g. So I find the square root, I find the reciprocal and I find the square root both sides, and that gives me the expression for the period, which means I can also find the expression for frequency. So the frequency would be the reciprocal of that. So the expression for frequency f will be equal to 1 over 2 pi. It would be 1 over 2 pi, and this would be square root of, we get the reciprocal, a rho g divided by m. So you can try the same with this, you can try the same with that, and you'll be able to find the expression for period and the frequency. That is for a floating cylinder. So a floating cylinder can be made to oscillate up and down so that it approximates simple harmonic motion. Okay, let's see the third example. The third example is going to be oscillation of a liquid in a U tube. Of course, a liquid in a U tube can also show simple harmonic motion. It can oscillate up and down. Let's consider a U tube in two positions or in two situations. The first situation, the tube is open to the atmosphere and the tube is not disturbed, so that the liquid in both arms is at equilibrium and the liquid is settled. Because on both arms we have atmospheric pressure, so the pressure on both sides is going to be the same. So it means the liquid will be at the same level since on both arms we have atmospheric pressure. So at equilibrium, in this position here, we are at equilibrium. So at equilibrium, what is the mass of the liquid in here? Remember, the mass of the liquid is going to be equal to the density times the volume of the liquid. To find the volume of this liquid, we shall take the cross-sectional area of the cylinder. Let's say the cross-sectional area of the cylinder is A. So the mass of the liquid at equilibrium is going to be equal to the density cross-sectional area times the length of the liquid L. So let's say the length of the liquid column at equilibrium is L. So this is going to be the mass of the liquid at equilibrium, rho A times L. Okay, so we are now going to consider the second position when, or at an instant when the meniscus on the left-hand side has been pushed down by maybe an external force. And then the external force is released so that the liquid now oscillates up and down. So consider the instant when the menisci are a distance x from the equilibrium position. So we have pushed it to a distance x above the equilibrium position on the left hand side. So it has moved a distance x below the equilibrium position on the right hand side. So the total distance through which the meniscus is on the left hand side is equal to this distance here, which is twice of x. That means the pressure on the left hand side is greater or is excess compared to the pressure on the right hand side due to this height here. So this height gives us the excess pressure on the left hand side as compared to that on the right hand side. That height gives us the excess pressure on the left hand side as compared to that on the right hand side. So it means the excess pressure is going to be equal to, of course, remember pressure is equal to, pressure due to the liquid is H density times G. So the H is going to be 2x. So this is going to be equal to, the excess pressure P is going to be equal to H density times G. So the excess pressure is equal to twice X, which is H, then times the density of the liquid, which I will call rho, then times G. That is the excess pressure. Then remember, by definition of pressure as force acting normally per unit area or force over area, it means force is equal to pressure times the area. So the excess force, which we are going to call the restoring force, or the resultant force, F, is going to be the pressure, which is 2x times density times G, then times the cross-sectional area, which is going to be A. Okay, so we're now going to employ Newton's second law. But remember, the restoring force or the resultant force is going to be acting in the opposite direction to equilibrium, because the opposite direction to displacement, because if we push this downwards, it makes this liquid on the left hand side rise upwards, which means the restoring force is going to be downwards. It immediately brings the liquid back to tend to bring the liquid back to equilibrium. So I am simply saying that F is going to be equal to the negative. You must explain why you bring in the minus. The minus implies that the restoring force is in the opposite direction to the displacement. So this is going to be minus 2. It is going to be minus 2x times density times g times a. And I'm saying the minus is just showing that the minus means force is in opposite direction. Opposite direction to force is in opposite direction to the displacement. Okay, so that's what the minus implies. So using Newton's second law, ma is going to be equal to negative 2x rho g times a. So the acceleration is going to be equal to negative 2 rho g a times x divided by m. So that is comparable to the equation for simple harmonic motion. If you want to compare with acceleration is equal to negative omega squared times x, which means that omega squared is going to be equal to 2 rho g a over m. What makes this equation to show that this is showing simple harmonic motion? 2 rho g a over m are constants. And if they are constants, it means acceleration is directly proportional to x. The minus indicates that acceleration and displacement are always in opposite directions, hence simple harmonic motion. So if we compare these two, omega squared is equal to 2 rho g a over m. But remember, omega is 2 pi over t. So I will simply say 4 pi squared over t squared is equal to 2 rho g a divided by m. I get the reciprocal and then the square root. I'm trying to find the period. So the period is going to be equal to 2 pi square root. Reciprocal was m over 2 rho g a. Now, a smart student will recall that from the first equation we saw that m was equal to density times a times L. That was m. So a student could also say that T is equal to 2 pi square root of, where there is m, they put rho a L divided by 2 rho g a, which means this could also become 2 pi square root of rho cancels, a cancels, so it becomes L over 2g. It could also be L over 2g. So that could be the expression for the period. It could be L 2 pi root L over 2g as the period. So you could express this in any other way. So then frequency is equal to 1 over period. So it will be 1 divided by 2 pi square root of m divided by 2 rho g a, or frequency could be equal to 1 over 2 pi square root of 2g divided by L. So whichever could be an expression for a frequency. So that is simple harmonic motion being approximated by a liquid in a tube. A liquid in a tube can oscillate back and forth. So it can approximate simple harmonic motion as we have shown there. Okay. Then maybe let's talk about now springs. Having seen floating cylinders, we have seen a liquid in a YouTube. How about if we talk about springs? So let's talk about springs. Springs can be arranged horizontally and vertically. Let's begin with the horizontal spring. A spring arranged horizontally like this one here and attached to a mass which can be made to oscillate back and forth. So let's consider a body attached on a spring. Let's say the spring constant is going to be K and the mass of the body is M. Now, if we displace the mass to the right-hand side through a distance x, of course, there is tension in the spring which tends to pull the mass backwards. That tension is going to be the restoring force. And you recall from Hooke's law, the restoring force is equal to K times x. But because the x in the opposite direction to displacement, we shall put a minus. Do not forget to define the minus. The minus indicates, or the negative implies that the restoring force is in the opposite direction to the displacement. So the minus indicates that F is in opposite direction to X. Then you will recall Newton's second law. By Newton's second law, when I write N2, that is Newton's second law. So MA is going to be equal to negative Kx because by Newton's second law, force is equal to MA. So it means the acceleration is going to be equal to negative of K over M then times X. Of course, this is going to be simple harmonic motion because K and M are constants. So A is directly proportional to X. The minus indicates that A and X are always in opposite directions, hence simple harmonic motion. So we can compare. With A equals negative omega squared X. So let's try to compare with A equals negative omega squared X. It means the omega squared is equal to K divided by M. Omega squared is K divided by M. And if that is true, remember omega is 2 pi over T. So I'll just put there 2 pi over T, which becomes 4 pi squared divided by T squared equaling to K divided by M. When I get the reciprocal and the square root, so T is going to be 2 pi square root of M divided by K. So that will be the period. And of course, the frequency is just obvious. The frequency will be the reciprocal of the period, which will be 1 over 2 pi square root of K over M. So a mass attached on a spring, which is horizontally laid on a surface, it can approximate simple harmonic motion. But however, we must take an assumption that the surface is extremely smooth. So this should be a smooth surface so that friction is negligible. Otherwise, friction would cause what we shall later on call damping. That is, friction will cause the energy of oscillation to be wasted so that the oscillations take a very short period of time. So that's what we shall call damping later on. So that is a mass attached on a spring horizontally. The same thing can be achieved if the mass is attached on a spring in the vertical plane. Let's consider the vertical plane. So a body or a mass is attached on a spring in a vertical plane. We can just consider the same mass M attached on a spring in the vertical plane. So here I gave three scenarios. In the first scenario, there is no mass attached. So the spring has its original length. In the second scenario, a mass has been attached so that the spring stretches, but there is equilibrium. In the second, in part two, the spring has been stretched, but there is equilibrium, so there is no restoring force here. So in this case, in the first case here, there is tension T1 in the spring, but the tension T1 at equilibrium, it balances with the weight mg. So it means tension T1 here is going to be equal to mg in that case. But I want you to remember that the tension is given by Hooke's law. Remember the tension T1 is equal to K times E. That is it is equal to the spring constant times the extension. So the tension is equal to Ke. So I can simply say mg is the same as Ke for equilibrium position. So this is in equilibrium in part 2. Then in part 3, we displace the mass even further through a further distance x, which means we increase the tension. According to Hooke's law, the tension is directly proportional to this extension. So the new tension here, which I'm going to call T2, is going to be the constant K into the new extension, which is going to be E, plus a further distance x. Because the displacement is downwards, the restoring force is going to be in the opposite direction, trying to pull back the mass towards equilibrium. So that calls for a minus sign that I'm going to introduce later on. Okay, so the resultant force is going to be the difference between T2 and the weight. So here T2 is greater than mg. So the resultant of those two is going to be the restoring force. So the restoring force F, or the resultant force upwards, is going to be the restoring force. So the resultant force F is going to be equal to T2 minus mg. That is the resultant force. So this is going to simply be equal to T2, which is going to be K into E plus X, then minus mg. So the resultant force is going to be equal to Ke plus Kx minus mg. But remember, Ke was equal to mg, so the resultant force is the same as mg plus Kx minus mg. So this cancels with this. So this is the resultant force. However, I will say F is equal to negative Kx, and I explain the minus because F is in the opposite direction to X. X was vertically downwards, the restoring force is upwards, so I must introduce a negative. So still by Newton's second law, MA is going to be equal to negative Kx, and we have already seen A would be equal to negative K over M times X. We have compared with A equals to negative omega squared X, and it meant that omega squared was K over M, which meant that omega is 2 pi over t, so this becomes 4 pi squared over t squared, being equal to K over M. Then when you get the reciprocal and find the square root, we saw that t was equal to 2 pi square root of M divided by K, and then F is 1 over t, which is 1 over 2 pi square root of K divided by M, as we have seen in the previous example. So whether the body is horizontal, whether the spring is horizontal or it is vertical, as long as it is alone, the expression for acceleration the expression for simple harmonic motion is the same as we saw. The period and the frequency are going to be the same as shown here. So it doesn't depend on whether it was horizontal or it is vertical in that case. Okay. So that is a mass on a spring, but this time it is vertical. Let's now try to combine springs. Let's try to combine springs. So let's consider horizontal springs connected together with the mass at the end. The mass is at the extreme end. The mass is at the extreme end of the two springs. How do they behave? Of course, we know that the mass will oscillate if the surface is smooth. So how do they behave? This is what I'm talking about. You have two springs which have been joined in series, and a mass is attached to the extreme end. Now, the easiest way to do this is to think about the effective either spring constant, or to think about the effective extension in when the mass is given a displacement to one end. So if the mass is given a small displacement, say x, to the right hand side, each of the spring is going to extend so that total extension is actually the sum of the two extensions. But the tension in each spring is still going to be K times E if the springs are identical. So for this curriculum, we shall consider the springs as being identical. So the tension here in this spring is going to be K times E. The tension here is going to be K times E in each case. These experience the same tension if you cause a displacement X to the other side. So the restoring force is going to be the same for both springs and is equal to the tension in each of these springs. If you cause a displacement X if you cause a displacement X to the left to the right hand side, each spring is going to experience a tension which is equal to K times E. The same tension experienced by this spring is the same tension which is expressed by this spring, which is going to be the same as the restoring force, because to bring back this mass to equilibrium, you must remove that tension. You must remove the same tension, which is equivalent to removing the same tension from both of the springs. Alternatively, you could think about it in this way. For example, when you cause a displacement X to the right hand side, you have caused a displacement X to the right hand side. The total extension X becomes E plus E, which becomes twice E. And the tension, remember, in each spring, tension in each spring is equal to K times E. That is tension in each spring. But remember, I said the restoring force is going to be the same as the tension in just one spring, because it is the same tension which is experienced. So the restoring force F is going to be equal to the negative of just K times E, because remember, each spring experiences the same force, which is K times E. Of course, you explain the negative. The minus means that F is in opposite direction to displacement. Okay, so remember, X is equal to twice E, so I have to remove E and bring in the X because this was displaced through a distance X. So if I bring in X here, X was 2E, so where there is E, I'm going to put there X over 2, so it means F is going to be equal to negative K X divided by 2, because E is going to be X over 2. Okay, so by Newton's second law, MA is going to be equal to negative K over 2. So it means the acceleration is going to be negative, there's an X here, negative K over 2 times M. And if you compare with the expression A equals to negative omega squared X, you will notice that omega squared is going to be equal to K over 2M. But remember, omega is 2 pi over T, so I'll say 4 pi squared over T squared is going to be equal to K over 2M. So we cross multiply and find the square root. So this means T is going to be equal to 2 pi square root. 2 pi times the square root of 2M over K, which means the frequency is going to be 1 over 2 pi square root of K divided by 2M. Okay. Alternatively, the easiest way to think about this is to find the effective spring constant. If these springs are identical and they're in series, we treat them as if they were resistors in parallel. So total constant, I'll call it K total, is equal to the product, which is K times K over K plus K, which is, so we get them from 1 over total constant is equal to 1 over K plus 1 over K, which is the same as 2 over K, or which is K squared over 2K, which is simply K divided by 2. That is total constant. Effective extension of course is equal to x because the system has been displaced through a distance x. So I will just combine total constant and x. So F resultant force or resultant tension is equal to total constant times total extension. But because it's in the opposite directions, I just put a minus there. So this means F is equal to total constant, which is going to be K over 2, then times X. And then I introduce Newton's second law. So the easiest way is to just think about, this is extension. The easiest way is to think about the effective constant. And since X is the effective extension in if the displacement is, if the springs are in series and displaced further through a distance x, it means each of the springs stretches through a distance e plus e, which when we sum them up, we get total extension, which is x. So if x is the effective extension, we just need the effective constant and combine the two. So F is going to be effective constant times the effective extension. So that gives us the same thing. So you can think about it in this direction. Okay, now let's fix, I think we should now fix the mass between the two springs. So we have a horizontal springs, this time with the mass between them, as shown here. So in the first case, in the first scenario, we have the mass is trapped between the two springs, whose spring constant is K. But of course, it is impossible, nearly impossible, to trap a mass between two supports or two fixed ends without causing an extension on any of these springs. If they are identical, we can assume that the extension caused in the process of trapping the mass between the two springs is going to be E, equilibrium extension, when the mass is trapped and it's not moving. So the equilibrium extension there is going to be E in that case. In the second case, when we now displace the mass to one side, let's say we have displaced the mass to the right hand side through a distance x. The extension, when we move the mass to the right hand side, the extension here becomes E plus x. Yet the extension here becomes E minus x, because on the left hand side it compresses, it stretches, yet on the right hand side it compresses. So if the mass in the figure is displaced through a small distance x, say to the right, as we have shown in this diagram, one spring extends by x, the other spring compresses by x, by the same amount x. So the tensions here, the tensions have now changed. So the tensions, I will say T1, the tension forces in the springs are going to be, so tension forces are T1 is going to be equal to K into E plus X. And then T2 is going to be K into E minus X. So those are the tension forces in the spring. So the resultant force on this mass is the one which brings it to equilibrium. So it is going to be the difference between these two tensions. So the total resultant force, so the resultant force, is going to be equal to K into E plus X, then minus K into E minus X. That is going to be the resultant here. So I think the resultant, when you subtract here, that is KE plus KX minus KE plus K. So this is minus KE plus Kx. So this one cancels out. So the resultant force F is going to be equal to K times X. That is the resultant. K times X. no, it is 2k because it is kx plus kx, which is twice kx. So that is the resultant force. But remember, the resultant force acts in the opposite direction to the displacement, because the tension to the left is going to be greater than the tension to the right. So the resultant force is acting in that direction. So I will simply say that F is therefore going to be equal to negative 2kx. So I explain the minus. The minus means that F is in opposite direction to x. So then I talk about Newton's second law. So by Newton's second law, the force is Ma is going to be equal to negative 2k times x. So I divide by m, so A is going to be negative 2k divided by m, then times x. So compare with the general equation of simple harmonic motion, which is A equals to negative omega squared times x. So it means omega squared is going to be equal to 2k divided by m. Omega is 2 pi over t, so I just find omega is 2 pi over t, so I will just substitute it here, so it becomes 4 pi squared divided by t squared equaling to 2k divided by m. Reciprocal and square root gives me t as twice pi square root of m divided by 2k. If I try to find the frequency is going to be equal to the reciprocal, so it will be 1 over 2 pi square root of 2k divided by m. Okay, so that is for mass for an object which is trapped between two springs and then displaced so that it oscillates back and forth. That is simple harmonic motion. And maybe let's have now the springs in series, but this time they could be in the vertical plane. Suppose the springs are in series as we have mentioned, but they are in the vertical plane. In series combined, but in the vertical plane. We have been seeing a horizontal. Let's see when they're in the vertical plane. Let's consider two springs combined in series, but in the vertical plane. Now, like I said in the previous example, the easiest way to think about this is find the effective extension and the effective. If you can find the effective extension, but that would take much time. If I know that if the system is given a further displacement x below the point of equilibrium, then it means the effective extension is going to be x, which is the sum of the extension in each of these springs. Then total constant is going to be the effective constant for springs in series using your ideas of AS. For springs in series, I think I've just mentioned for springs in series, 1 over total constant is equal to 1 over k plus 1 over k. So 1 over total constant is equal to 2 over k, which means total constant for springs in a series is going to be k divided by 2. So the effective force or the effective total tension in springs when they're joined in series like that is going to be equal to the total constant times the effective extension, total extension, which is x, because when this is given a displacement x is a combination of E plus E. So the total extension is x. Okay, so that means that the resultant force is going to be k total, which is k divided by 2, then times the extension x. So, but remember, F is acting in the opposite direction to the displacement. I've considered the system given a further displacement x below the equilibrium position. That means x is a sum of E plus E. So, by Newton's second law, the force is going to be Ma, or I can introduce a negative here, and I say that F is equal to minus k times 2, k over 2 times x, then I have to define the minus. You have to define the minus. The negative minus means that f and x are in opposite directions. Okay, they are in opposite directions. Okay, so it means MA is going to be equal to negative k over 2 times x by Newton's second law. So the acceleration is going to be negative k over 2, then times m, then times x. We are going to compare with a is equal to negative omega squared times x. So the acceleration, omega squared, is therefore going to be equal to k divided by 2m. But remember, omega is 2 pi over t, so I will simply say 4 pi squared over t squared is equal to k divided by 2m. Reciprocal and square root. T is going to be equal to 2 pi square root of 2m divided by k. Then if I want to find the frequency, it is also going to be reciprocal of t, which is equal to 1 over 2 pi square root of k divided by 2m. As simple as that. So for springs in series, if you can arrive at, or for a combination of springs, if you can obtain the effective constant, then it means you are good enough to go. You don't even need to use a lot of mathematics here. If I can find the effective constant, then I've already found the restoring force, because the restoring force is going to be determined by the effective extension and the effective constant. Okay. Then let's now consider two springs which are joined in parallel, springs in parallel. So we have two springs which are in parallel. We shall only consider if identical springs. So let's consider two springs which are in parallel, and in equilibrium, each could be having a spring constant which is going to be E. But we are going to assume that these are given a further displacement x. These are displaced through a distance x below the equilibrium position. So the extension that will be caused in each spring is still going to be x. If I pull this system through a distance x, this will stretch further by x, the other one will also stretch further by x. So the effective extension in the vertical is still going to be x. Because they're in parallel side by side, the effective extension is not going to go beyond x, it's still going to be x. But from your ideas of a spring combination of springs in the formation of solids in AS physics, the total constant for springs in parallel is simply the sum of the individual constants. So I'll simply say total constant K total is going to be K plus K, which is equal to twice K. That is total constant. So the resultant or the effective force on the springs of the system is going to be the total constant times total extension. Total constant times the total extension. So the resultant force on the system is going to be twice K times X. In other words, the restoring force becomes even bigger for springs in parallel. So this means I will just introduce a minus and say F is equal to negative 2K times X. And we know what the minus implies, so I'll tell the examiner that the minus implies that F is in opposite direction F is in opposite direction to X. F is in opposite direction to X. And in that case, I can now introduce Newton's second law, which is MA. F is equal to MA. So I'll say MA is equal to negative 2 times KX. So which means A is going to be equal to negative 2K divided by M, then times X. Of course, 2k and m are constants, which means a is directly proportional to x. The minus indicates that a and x are in opposite directions, hence that is simple harmonic motion. So all I need is now to find the period and the angular velocity. I mean the period and the frequency. So I will compare with a equals to negative omega squared times x, where omega squared will therefore be twice k divided by m, and omega is 2 pi over t, so I'll say 4 pi squared divided by t squared is equal to 2k divided by m. So we get the reciprocal and the square root. So t is going to be equal to 2 pi square root of m divided by 2k. If I want the frequency, it is the reciprocal, so it will be 1 over 2 pi square root of 2k divided by m as required. So those are, I think those are enough combinations. Those are enough combinations, and I think this should, lesson 2 should stop here. It was longer than I expected. It was longer than expected, but before we finish lesson 2, let's compare circular motion with simple harmonic motion. Let's try to compare now circular motion to simple harmonic motion. Okay, so in comparison now, we have seen that for circular motion, the radius of the circle is r. I need to pick a pen. For circular motion, the radius, we consider the radius to be r. And for simple harmonic motion, the radius could be equivalent to the maximum displacement, which is the amplitude. In circular motion, we talk about angular velocity. In simple harmonic motion, angular velocity can also be called the angular frequency. In circular motion, we saw that the maximum speed of v was equal to omega r. In simple harmonic motion, the maximum speed was omega x naught. Of course, remember x naught could be equivalent to r. Then acceleration could be omega squared r for circular motion, which was centripetal acceleration. And for simple harmonic motion, we saw that the maximum acceleration is negative omega squared r. But I said in calculation, we take the magnitudes. So for circular motion, we may talk about one revolution. And for simple harmonic motion, many times we may just refer to one oscillation. That is for simple harmonic motion. Some of the things we need to note from what we have just covered, you should be able to relate to circular motion to simple harmonic motion. Some equations operate the same way. We also mentioned that S was equal to R times theta for theta measured in radians. I think we saw that under circular motion. And you must be able to define a radian. One radian, the angle is defined as 1 radian if the arc length is equal to the radius. You should be able to use V equals to 2 pi over R, because remember V is equal to omega times R, and omega is 2 pi over T. You should also come up with appropriate simple harmonic equations for given questions. For example, timing starts when the body is at equilibrium. Timing starts when the body is at maximum displacement. You should also be able to use the equation A equals to negative omega squared times x, and of course the one for velocity, which is v equals to plus or minus omega square root of x naught squared minus x squared. You should also be able to use that expression. You are going to be able to calculate the maximum acceleration and maximum velocity. We have seen expressions for maximum acceleration and maximum velocity. You should be able to define simple harmonic motion. By this point, you should be able to sketch graphs of displacement time, velocity time, acceleration time. We have sketched velocity displacement. We have sketched acceleration displacement. You should be able to, we sketched displacement time, velocity time, and I gave you an assignment to sketch acceleration against time, and you should be able to do that. Then, of course, the graphs of force. Force against displacement should also be, because it is the same as the graph of acceleration against displacement. Then acceleration displacement graph, that one we sketched, and velocity displacement graph, that one we have also sketched. Maybe you should just be able to test yourself before we go to the last point of energy. A load of 7.0 newtons causes the spring to extend by 5 centimeters. Calculate the spring constant. Total load required for the spring to extend to 7 centimeters. So you should be able to test yourself here. This is essentially Hooke's law. F equals to K times X. So we want to find K. They gave you the load, they gave you the extension. You should be able to do that. K equals to the load divided by X. K is equal to the load, which is 70, divided by X, which is 5 times 10 to the power of minus 2. So that it gives us our constant in newtons per meter. I think that is 70 divided by 5. So this is 1,400. Then the load required for the spring to extend to 7 centimeters. So F is equal to K times X, where K is 1,400 times X, which is 7 times 10 to the power of minus 2. I didn't want to do this because this is AS, so this would be 98 newtons. When the spring is oscillating with a load of 70 newtons, calculate the period. Of course, to find a period, you have to think about the expression for the period. Of course, we derived this equation. I don't want to derive it again. I'll just use it there. The period is going to be 2 pi square root of m is the mass, but they said when the spring is oscillating with a load of 7 newtons, calculate the period. The mass is going to be the weight or the load divided by g. So this is going to be 70 divided by 9.81. So this will be 70 divided by 9.81 times K, which is 1,400. So we have 70 divided by open brackets 9.81 times 1,400. Then I find the square root. Then I multiply this by 2 pi. And this is 0.449 seconds. Then the angular frequency, of course, we know that omega is 2 pi divided by t. So I just divide 2 pi by 0.44. And this is giving me 14 radians per second. Then the natural frequency of oscillation of the spring. So we know that omega is equal to 2 pi times f. So this means that f is going to be omega, which is 14, divided by 2 pi. And this is 2.23 hertz. Okay, so that is a simple takeaway here. So let lesson 2 stop here. I'm very, very tired. Let lesson 2 stop here. We shall start lesson 3 from here. Until next time, bye bye.